Dr. John Hathaway. So it's a real pleasure to be joined by such an illustrious character today. We decided I'd go first, and I'm going to talk a little bit about stormwater control measure resiliency. I'm going to make an immediate plug since we have 460 something people coming to please consider attending next March. I think it's like 14th through 16th. The ASCE EWRI Operations, Stormwater Operations and Maintenance Conference. It's going to be in Wilmington, North Carolina. It is hosted by NC State. And if you are joining us from a municipality in North Carolina, there's actually going to be a reduced rate for you to come in. I negotiated with ASCE to get y'all a reduced registration fee. But the reason I'm saying that associated with this presentation is that there's a couple of themes in it, and one of the themes is maintaining in the light of big storms and how we deal with resiliency as a part of maintenance within the stormwater world. So if you're on this webinar, you'd probably be really interested in that conference. Plus, there's going to be a riverboat ride, and I mean, really, can you really beat that? All right. So with that, this work really got its start after Hurricane Florence smashed into North Carolina and South Carolina, bringing with it some winds, but really a lot of rain. As all of y'all remember, it was pretty slow moving, and it had the distinction of turning highways into rivers. And I'm not going to show this, but this was an NCDOT drone. Let's see, NCDOT drone footage of I-40. It looked like it just become a river. And in my mind, probably the most apocalyptic photo I've ever seen from North Carolina was taken during this time, where we have this picture of fish. Let me see if I can, for some reason there it is, where fish were found after the water drained off I-40. They had just fish all along I-40. I mean, I'm telling you that if there's not a sign of the apocalypse, I don't know what is, right? And a lot of y'all probably remember watching the videos of the firefighters like blowing the fish off with water from I-40. Things you never thought you would see. And we had massive numbers of road closures. Wilmington became an island for a little while there. The Navy was consulted about airdropping materials into the city. I mean, just crazy stuff that I don't know, we weren't taught that this would happen, certainly not in school. Or if we were taught it would happen, I don't know if a lot of us took it seriously. And then, as they say, the beat continues. I saw an entrance text or a chat in here about what a timely webinar. Absolutely, and Fred has passed through, and I'm sure John, Eastern Tennessee, I imagine, got hammered just like Western North Carolina did. And these are roads, and remember, not only these roads, but these are people, these are livelihoods, and they're being impacted by these massive storms that just seem to smash into our state, dump lots of rain, and harm a lot of people and livelihoods, and even lead to death. So clearly, there's a lot that needs to be done about it. And one of the things I want to lead in with is that it's not like our politicians haven't noticed. And very recently, just 2 months ago, I was a part of a larger team that was organized by some folks at UNC Chapel Hill on a flood resiliency study for the North Carolina Policy Collaboratory, and working with several researchers from across several institutions. This report was given to the General Assembly, and this was done obviously in light of Hurricane Florence. And some of the things that they did is they came up just to try to hammer home how impactful these storms were. So you see, like, and these are not just Florence, right? We're talking about Hurricane Matthew, and now we're looking, of course, at the remnants of Tropical Storm Fred. But 100,000 buildings damaged in a storm, or really, probably for me, the most incredible thing was a yard, not a foot of rain, a yard of rain in Elizabethtown, North Carolina. But and a very important part of this report, and the reason I'm hammering home on this a little bit is that it's available to any of you. You don't even have to be North Carolinian, but if you are North Carolinian, all you have to do is you can Google the North Carolina Policy Collaboratory Report, or you can call your local Congress, local legislator, and ask him for a copy, because ask him or her for a copy, because they all got one. They all got one. And one of the, I think the important things is that there were many findings that came out that have the, if they are implemented, have the ability to curtail, to some extent, impacts from the next big storm. And I'm going to share with you what the stormwater team of NC State's part or contribution to this study was. All right. And so what the part I'm going to share with you all today is the results of a survey that we undertook with professionals. You can see the types of professionals here who do work in East North Carolina. And we wanted to make sure, it is an important point, that the study was particularly funded to focus on East North Carolina. It's not as if the Piedmont, and certainly as demonstrated today, the mountains of our state don't get hit. We obviously do have to deal with resiliency issues there too. But this did have a focus of East North Carolina. But keeping that in mind, the findings I'm going to share with you, I think, are applicable across the state. But we got a variety of folks that were involved in the world of stormwater. And it was a really wonderful thing because it was this free flow conversation. And y'all who know me know I like to converse. And so I just was loving it, man. Just talking stormwater for an hour over lunch. Doesn't that sound fun? But a lot of y'all like, why didn't you ask me? Look, COVID. That's why not everyone got asked, right? But what was really fascinating is through our free flowing conversations, there was a lot of repeat comments. And it was and you'll see here in a second, and we got folks from Wilmington, people who are active in the northern Outer Banks, people active in the middle part of the state, like the Jacksonville area and Morehead City. And we were hearing the same type of comments from people involved in maintenance, people involved in design, and even a couple of folks who work for cities and municipalities. And so for me, the report actually became pretty easy to write. And I don't know if I expected that when we started, because there was just so many themes that kept being repeated. And so we could boil it down. And I need to point out that this work was done in conjunction with a grad student of mine. His name is Mr. Caleb Mitchell. Caleb actually just joined NC State as an extension associate. So he's now not just a PhD candidate, but he's earning more money, obviously, is what he's doing as an extension associate. But there's basically, we came up with this thing called the resiliency fundamentals. And the resiliency fundamentals are honestly pretty darn straightforward. They are, number one, if a stormwater control measure is appropriately sited, well-designed, constructed as that design intended, and, drum roll, I don't know if y'all can hear that, reliably maintained, then guess what? It is likely to be a more resilient stormwater control measure than not. All right. And I don't think there's anything in that you're like, well, duh. But I do have a question for you, and I'm going to ask people to come off the chat to respond to this. Which one of these four would you guess is the weakest link? So conjuring that television show, the weakest link. All right. I see someone is maintenance, all of the above, maintenance for maintenance. You guys are killing it. You're killing it. That's great. It's either for or maintenance. They happen to be the same thing. Yeah, great job, Kristen. Maintenance. And it was clear. Like, there wasn't a single person that we interviewed that was like, yeah, I think the biggest issue is they're not being designed right. Now, it's not they're not design issues, but the biggest issue was maintenance. And the reason the reason we believe that maintenance is the most problematic thing is that we're just not talking. We're just not talking. All right. So you think about it, there's the baton handoff between the person who does the siding and the design. Well, that's usually the same person, right? And then the person who did the design is often involved, usually involved with the construction, all right? And so all of it makes sense. But then all of a sudden, this constructed thing is there, and then it becomes the purview of a property manager, right? Who probably doesn't know a whole lot about stormwater because they know a whole lot about a lot of other things. So it's just that the communication between basically the handoff between the designer or contractor and the property owner is not being made. And then, very importantly, and while this is not true across the board, because there are a lot of communities in our state that certainly are enforcing the need for maintenance, when it's not being enforced, unmaintained practices are apt to fail. So the maintenance is either isn't being done, or probably more often is not being done appropriately. Okay, which now gets us to the 4 fundamentals. And I will spend some time going through each of these fundamentals and basically elevating some what I call the highlights. All right. So the first thing is, and I know sometimes we're tempted based upon numbers, like nutrient removal numbers, if you're in the Neuse River Basin, to force stormwater control measures in places where, Mother Nature's saying, I don't think it belongs here, guys. All right. So recognizing that there are practices that are much better suited for high water tables. And then there's other practices that really need some separation. The infiltration-based practices need to have some separation. And basically forcing practices where they don't belong can be a problem in terms of how well the practice can hold up in the future when big storms hit it. All right. And then we have some switch hitter practices, but even the switch hitter practices do need to be designed appropriately. So bioretention cell can go in. It does obviously better in when you have a fair amount of separation between the seasonally high water table, but there are some designs that you could use in a shallower situation, but you got to make sure those designs are actually used. All right. So just knowing the types of practices that you're trying to put in and making sure that you know where your water table is a huge issue. And we have seen it multiple times before. So let's talk a bit about the water table. It has probably, of all things I'm going to share with you, I think it has the most dramatic impact on how well a stormwater control measure will work. So what I'm showing you here is a picture of a dry pond, okay? Anytime you see tire tracks and water expressing itself in a dry pond, I'm a big fan of rules of thumb. Here's a rule of thumb for you. It's probably not working right, okay? The dry pond really doesn't want to be a dry pond, all right? So we want to make sure that as a part of the FCM design process, that an appropriate professional is brought on board to determine where that season high water table is. All right, that's not something that's just like lip service. It really matters from a resiliency standpoint. Now, I'll explain a little bit more how this impacts resiliency in a couple slides. And it is also very important to remember that we need to also consider, if you're going to err on the side of something, try to err on where it's going rather than where it is. Meaning, a lot of times when we're building something, we're knocking down trees, all right? And if you go ahead and you find out where the water table is before you cut down trees or immediately after you clear and grub, you're going to have an artificially low water table determination, because those trees were doing an awesome job for us in terms of pumping water out through evapotranspiration and essentially keeping a water table further away from the surface. Once those trees are replaced by buildings and parking lots, then, well, the water table is going to rebound and come closer to the surface. So try to keep that in the back of your mind, that the water table, the way we develop is likely to be higher to the surface than when you first measure, particularly if you're taking a look at it when it's in a wood state or right after it's been in the wood state. The other couple things that are really, really important is knowing what's going to be happening around your practice, all right? So if you do have a stormwater control measure, that is near an agricultural area or is near where you can expect wind to blow stuff in, all right, or is part of a development that has out parcels that are going to be, at some point constructed, those can have pretty big impacts on how well your stormwater control measure works. And then particularly important along the Outer Banks and our barrier islands, but also kind of near coastal rivers, understand how surface waters might impact that stormwater control measure. And I will get into a real quick personal experience with that. There was a wetland, I think you'll see a picture of it right here. Yeah, there's a wetland that NC State designed and working with a grantor had built in a town in New Bern, actually in Riverbend outside of New Bern, North Carolina. And it was fine. It was fine. And then a tropical storm came and it started blowing, right? You know how they do. And water started getting pushed up. All right. So the water was blown and was pushed up into the harbor where it was continued, then pushed into an area where the wetland was located. And the water lily, I should point out, brackish water, ended up filling the wetland. All right. Now, in the process of doing that, all of our freshwater plants in the wetland, well, they were exposed to brackish water for multiple days. And you can probably guess what happened to a good chunk of that vegetation, but it died, all right, because it just wasn't able to either, one, withstand the excess inundation, but also I'm pretty sure that the brackish conditions didn't help. So understanding how like your adjoining water bodies quote behave, all right, is a key part of designing a practice that's not going to fail. Okay. So there you go. So this is why siting practices really matters. All right. So that the vegetation has a profound impact on how well a practice is stable. All right. It helps determine resiliency. And if you lose your vegetation and you end up having exposed earth, then you're going to have a much less stable practice because obviously, exposed earth is very much apt to erode the next time we have a big storm or even kind of a medium-sized storm. All right. So there is a reason I'm sort of harping on plant survival and stuff like that, is that the plants really have a profound impact on sustainability or resiliency of a stormwater control measure. So let's move on now to the second great fundamental, and that is designing them correctly. All right. One of the things that did come out, and I'm glad to say this since we're on a DEQ webinar, is that the DEQ really laid the groundwork for successful stormwater control, resilient stormwater control measures by having the minimum design criteria. Like if we follow those minimum design criteria, that's going to get us 90% of the way of having resilient practices, which I thought from a design standpoint, which I thought was really fantastic. There were a few things that had probably the biggest impact in terms of emphasis that we should place on design. You can see a list of them. I'm going to actually just kind of plow through those pretty quickly. For one, in Eastern North Carolina, we usually have sandy soils. All right. And I know why we don't do this, but there is a reason that they have a 3-to-1 side slope requirement in there. And it is all about soil sloughing. And I know how so often I've even been associated with projects where we cheat on that 3-to-1 side slope. And when you do that, you're just inviting failure within your practice. All right. So sticking with that 3-to-1 side slope, and if you don't like it, then you can build a retaining wall. Obviously, it's more expensive, but if you want your practice to be resilient, let's adhere to these requirements to the side slopes. Secondly, when water is coming into a stormwater control measure, one of the things that has been pointed out is that if you can angle the water not basically away or certainly not directly into the berm on the back of the forebay, that helps preserve that berm. All right, so you can see here the runoff is actually shooting into the forebay at an angle that is almost directly opposite the berm. All right. And I see the berm, I'm talking on the back of that forebay berm. So that is a trick that, as much as you can, if you can employ that, that helps preserve that inner berm that that is an important part of the forebay. All right. The forebay, while it is really nice to, I'm one of those guys, I mean, if I don't have to use rocks, I'm not going to use rocks. But that doesn't mean you don't use rocks. There are times where riprap makes sense. And certainly making sure that the backside, you see this particularly, it's not that they put rocks all over the place, but riprap was certainly used to armor that dividing berm to make sure it didn't fail. If you've got another solution that you think is good and it will work, go for it. But make sure that that back berm of a forebay is appropriately armored or protected. Another thing that is great also from a maintenance standpoint is if you build outlet structures, which you do encourage to have them to be able to be walked out to, okay, or walked to, make sure that you have armoring around that outlet structure, because back eddies do form and they can cause erosion issues. All right, and again, that if you get erosion in around your outlet structure, that's a sign that it's not going to be particularly resilient for future events. So one of the things that came out is, well, you can read it right here, but perhaps the biggest design issue that was hammered home, was that we are not putting enough emphasis in our emergency overflow design. You know, it's just kind of the last thing goes, okay, I gotta make sure we put it on there, you know, because but the reality is that they're also not being built right. Like often they look like it's hard to see the berm or the weir aspect of them. All right, you can barely see it actually in this picture, but a lot of times the emergency spillways are just not, we're not putting the emphasis in them. The design criteria are there. We're just not particularly following them. All right. And another thing that was pointed out, I didn't realize this was an issue, but apparently in our neglect of considering spillway overflow, they've said that spillway overflow is sometimes just direct. I say directed. It's allowed to go to that the overflow channel is being sent away from properties that could get hit. And so a lot of emphasis, a key design point that I want to stress to folks is to make sure there is effort spent on the emergency spillway design. All right. We need to take that serious. And, you know, I think we used to think emergencies, well, I guess that might happen in my lifetime. The reality is we're getting emergency spillway used, you know, 2 or 3 times a year in some cases. Now let's move on to the third fundamental, construction. And I think one of the main take-home points we got here is that to be a good contractor in the world of stormwater control measure installation, you got to be able to wear a lot of hats. You got to know something about soils. You got to be working on utilities, but then you also know quite a bit about landscaping and aquatic habitat, right? So there's a lot that's going on that a successful SCM contractor needs to have some competence in. All right, and that honestly is a lot to ask. Okay, but there are I say it's a lot to ask. It's not as much to ask now as it was 15 years ago, because a lot of contractors actually do have that. The successful ones certainly do have that. So as the practice is being built, making sure that the vegetation is stable, that internal erosion, I talked a little bit about some of the design features like the back berm of a forebay, that's not happening, and just making sure that berms and dams are not failing. I mean, those are pretty obvious stuff, but still it matters a lot that this is being done. And so with respect to soils especially, it's a bit of a challenge because we have these compaction standards that are being brought in, that we have an expectation are going to be met, but at the same time, I keep talking about plants, and so the soils also have to be sufficiently fertile for vegetation to grow. So it's not a particularly easy task, I think. And it's also something that our designers need to make a point to be a part of, is take that seriously. And in your notes, like say, we have to compact it to a certain amount, but we also have to make sure we do some things to enable plant growth. In terms of construction, for example, if it's a water holding stormwater control measure like a wetland or a wet pond, then of course you can compact the subsoil. That's fine. but then you got to make sure you amend that soil so plants can grow. If it's an infiltration practice, then don't compact the subsoil. In fact, not only do that, step out and actually do things like to rake the soil. And NCDEQ has this stuff, this is available information, but remediate, scarify it, do something to encourage infiltration. And so you an example here of some topsoil being added. There are certain vegetation considerations. Y'all can look at those pretty quickly. But understand, and this again is hire or work with a professional who is competent in vegetation selection. All right. And that person is going to have to understand if the vegetation might be subject to brackish conditions, and would understand the types of plants to select. Certainly avoid monoculture. We talk about that, I feel like, almost all the time. And now we're going to close with what is the number one issue. All right. So, and what I mean by this is if we're going to be serious about stormwater control measure resiliency, we have to be serious about maintenance and stormwater control measures. I feel so strongly about that. I'm going to say it one more time. If you really care about SCM resiliency, you're going to really care about SCM maintenance. All right. And in that, there needs to be an enforceable agreement with the person that inherits the practice. And that person needs to understand, all right, or at least be told and have a document or something to refer to what is expected. Very, very big deal. Three things associated with maintenance that I want to hit on. One is to make sure that the hydraulic structures, the pumps, the valves are all working. That's a key part, all right? And then that ties into number two, and then we'll close on vegetation discussion. Pumps and valves, one of the main things that we want folks to understand is that pumps may have a new role in the world of SCM resiliency, and it's the idea of actually pumping down in advance of storm strikes, okay? If you think about it, a pond especially, and what do we have, 10,000, 20,000 ponds along our coast, right? A pond especially has capacity to mitigate certain size storm events. But if they're full before the storm hits, then their mitigation abilities are basically at their minimum, right? So what if you know a nor'easter or a hurricane is coming? You can actually start pumping 30 hours in advance, 24 hours in advance, and create excess storage capacity. And you're putting water into waterways at a time where that's the only water that's being put into waterways, right? It's not like it's being joined by bunches of rain. So this is a major thing and this is something that the policy collaboratory picked up on, is that the ability to create extra basin capacity by artificially lowering or pumping out practices in advance seems to be a really good idea. And it's something that coastal communities can do in advance. But obviously the ordinances have to be made so that works. And I think there needs to be some understanding as like when you're allowed to actually do the pumping, but in general, we think that's something that really needs to be done. And then you have to make sure there's not clogging. I mean, all of that obviously makes sense, and we talk about it, but if you do have inlets or outlets that are clogged, then you're going to encourage breaching, and that's obviously the last thing that we want. Because a breach practice is a totally non-resilient practice. It is dead to resiliency. And last but not least, just making sure that the vegetation is maintained appropriately. It makes a difference in terms of how well a practice will work in the long term. All right, let's see here. I apologize that my computer, here we go. My computer is struggling. All right, we'll get into allowing conversion at another point. So what are the main points from the study? First of all, as I mentioned before, the study really came out and said, hey, we think you should have communities authorize pre-storm emergency pumping. And something can be done in the short term, all right? And then there's a bunch of design features, kind of what I talked about, that should also be given some consideration. That's what the policy collaboratory pulled out. Now, these are three things that the dear Dr. Hunt wants to share with you, all right? Number one is that well-maintained stormwater control measures are more resilient stormwater control measures. Number two, well-vegetated stormwater control measures are generally more resilient than vegetated, generally, not always, non-vegetated. Last but not least, the more visible your stormwater control measure is, let's say it's in front of the store rather than tucked out back, it's likely to be better maintained, and therefore it is likely to also be more resilient. Last thing you guys to consider is that if you start putting practices up front and it forces you to make them look good, that actually can add value to property. And there's been some studies done at Clemson University that indicate that. So just South Carolina, just one state to the south, they're showing that that stormwater control measures, even if they're not particularly well designed, all right, or look good, they didn't tease that out, but they can add value to property, which is another reason perhaps to amenitize these things. So with that, we're going to go ahead and I'm going to turn this over to Dr. Hathaway, and we're excited to answer some questions towards the end. John's all yours.
All right. Hey, it worked. That's nice.
Isn't it?
You never know how it's going to turn out. Well, great. Thanks so much for having me. I was looking through the list of people attending, and lots of friends and colleagues from North Carolina on there. So good to see everybody virtually, and I hope everything's going over well over there. As Bill said, yeah, it's been raining like crazy in Tennessee. We've gotten about 2.5 inches, I think, just yesterday. So we had the tropical remnants that came through. So I'm going to talk about specifically focus in on bioretention a little bit today as we talk about climate change resiliency. And we've really worked mostly with bioretention because it's such a common practice and becoming even more and more common inside of cities for them to look to bioretention as part of their resiliency strategy. So a lot of people have worked on this over the past 3 years or so. Andrew Turpak is one of my former PhD students who works at Ohio State now. Anahita is a professor in systems engineering that I work with for data analytics. And then we had a recently graduated student here with a master's who also helped out on some of these elements. And so as we've talked about, right, we've got a lot of challenges in urban systems. And so I like to show people that, you know, it's not just climate change, it's also infrastructure degradation and population increase and development patterns. And so those things are really exacerbated by climate change, as Bill noted. I've been telling our incoming civil engineering students here that, you know, the nation is about to spend billions of dollars on infrastructure. And so we've got a lot of job security, hopefully, coming up here in the future. And so if we look at climate change and we start trying to delve into this idea of climate projections, you know, what do we see? And what we have is a lot of uncertainty, right? It's very challenging to determine what's going to happen in the future. What we know is that greenhouse gases are increasing. And so we can track that historically. We can look over what's happened with greenhouse gases. But projecting what's going to happen in the future is very challenging. And so if you've looked at any kind of climate data whatsoever, you've seen these representative concentration pathways. And this is kind of the way, or one of the ways that we deal with this uncertainty is by saying that our greenhouse gas emissions could follow a number of different scenarios depending on human interventions or lack of human interventions, right? And so these different RCPs basically show us, like, what will the future look like? In general, some of these lower ones are probably not going to happen, 2.6, for instance. But the ones that people look at a lot are 8.5 and 4.5. 4.5 indicates that there is some kind of intervention and we reduce greenhouse gases over time. 8.5 is a little bit more towards status quo, where things just continue on the same cycle, okay? But as I say that, you start getting a feel for this uncertainty, right? We don't know exactly how greenhouse gas emissions are going to change in the future. And so there is some uncertainty in there. The other thing is that extreme precipitation or precipitation patterns are not the same everywhere. This is some work from a colleague of mine, Josh Fu, who actually sits right next to me, who is another NC State grad, actually. And he is a world expert in air quality and climate change modeling. He actually used to work with Bill's dad at the EPA and RTP. So what he did is they basically took some climate projections and they looked at basically what does extreme weather look like? What does extreme weather look like under current conditions? So what's the upper 95th percentile of rainfall look like in different locations? What is that going to look like in the future? And then if we overlap those two things, how is extreme precipitation going to change? So the dark green areas means that we're going to get a lot more extreme or a lot more precipitation in those areas. The brown means that we're going to get less. And so we've done some studies with Ryan Winston in Ohio where we've looked at areas like this, and what they see in terms of climate change impacts are very different than what we see in the Southeast. So we have to kind of get a little bit of our head wrapped around. We're going to get differences depending on where we are. North Carolina and Eastern Tennessee, generally, we're going to, you see these similar patterns of more rainfall and more extremes. So I guess the question that we have is, we have uncertainty, and so what are we going to do about that? Do we wait until we have less uncertainty, or do we just decide to deal with it and engage with that? And so various places, this is back in 2013, places in Europe were already starting to look at design parameter changes in places like Belgium, where they start updating their design curves based on what they think climate change is going to do in the future. And so we see more and more and more of this. The cities are starting to update their design guidance based on these projections, but they are uncertain projections. So a few things we have to keep in mind. One is the spatial resolution of data. And I'm going to talk about that in just a minute. But it basically means that these global climate change models that people run are very coarse. And so the state of North Carolina, for instance, maybe 2 to 3 blocks may have 1 or 3 data points for the entire state. They're very large blocks that we look at. And so we often are taking measures to basically reduce those blocks into smaller blocks to get more basically fine scale data. The other thing is temporal resolution, right? So a lot of times when you look at climate data, it may be, let's say, daily or let's say daily resolution, right? And one of the things we have to deal with as urban hydrologists is that if you give me daily rainfall, what does that really tell me inside of an urban system? We know that in urban watersheds, things happen in a matter of, minutes, 15 minutes, 5 minutes, 30 minutes. And so having daily data doesn't really do a whole lot for us. Model verification is obviously challenging. How do you verify what you see in the future? A lot of times what these models do is they also predict historical weather patterns, okay? So if I have a climate projection that I'm doing, I am going to basically model historical data, and I'm going to model future data. And then I can actually test my model because I can see how well did it actually model historical data, and it gives me some indication of how it might function in the future. The other thing that we have to do is we have to engage with uncertainty. And we'll talk about how we've started to do that in just a minute. So global circulation models, like we said, very large block systems. And so a lot of what we do is that we take these inputs from global climate models and we put them in things like regional climate models, okay? There's different ways that we can downscale what we call our data. We can either do it statistically, or we can do that through local weather models. Okay, but the bottom line is that we're getting really good at that part of it, right? This is some data from Oak Ridge National Lab, which is down the road from us here. And what they're doing is they're able to get much more fine scale resolution. So this would be, let's say, a 4-kilometer resolution of data. This is 1 kilometer fine scale, more fine scale spatial resolution. So we're doing really good on spatial resolution of data. Temporal resolution is still a problem, okay, because it's very hard to predict anything at a fine scale. So a lot of times the data that we're working with is hourly at best for climate projections. And again, that's not perfect for urban systems, but is hard to go much more fine scale than that. Okay, so you think about what these models are doing. They're essentially saying, what's our greenhouse gases going to look like in the future? And then I'm going to put it in this Earth surface model, right, that takes into account weather patterns, and it takes into account conditions in the Arctic, and it takes into account conditions in the ocean. And so these are gigantic models that take huge, I mean, when they're running stuff like this at Oak Ridge, it's on, some of the world's fastest supercomputers that they're using to generate this kind of data. All right. So luckily, we are getting more and more publicly available data where it's not as hard as it used to be to get information like this. So what we've relied on is this NA-CORDEX, which is North American Coordinated Regional Downscaling Experiment. And what they've done is they have done a lot of this work for us. They've taken a bunch of different models of global climate models and downscaled them to more local conditions. You can get future projections. You can get historical projections. That's the modeling system that we've been using a lot. So I'm going to talk a little bit about how things are going to differ throughout the U.S. In terms of these climate models. So what are we using? We've got 10 different models that are available in that data set. You can see they've got some of them have the same global climate model, right? But they may use a different regional climate model, okay? Or it may be a different RCP. And so they all basically indicate one possibility of what future climate is going to look like, all right? But there's lots of different possibilities based on how you combine a global climate model with a regional climate model and which concentration pathway you choose, all right? The next step is that data itself has issues. And so this climate data is notoriously, has this drizzle effect, is what we call it. And what it means is that it tells you that there is a ton of little tiny events that have happened, which are often just noise. It's not correct data. So we do what we call correcting or model bias correction. So we've taken this methodology from McGinnis, and basically what it does is it tries to take this data and make it conform more to historical data. It takes out that small drizzling effect that we see. And so it's just a way to take our raw data and basically redistribute it so that it makes sense with future conditions. So it's a way of basically correcting that data to get rid of some of that drizzle effect that we see. Okay. So what we did is we took these 17 locations. They're all representative of one basically region. Okay. So these regions over here. Okay. And then we pulled those out and we run these models, or we pulled that data for each one of these locations to see what it looks like. And what we want to point out here is that this red block right here indicates historical conditions. I think I've got it laid out somewhere here. Well, we'll get to that in just a minute. But the red line indicates basically historical data. And then we look at what does a future climate look like is basically some percentage of that. So it's either plus or minus. It's either changed by negative amounts or it's changed by positive amounts. and it's changed by some percentage. And we do that just because these raw values start getting out of hand on us. And so this box plot here basically is all 10 of those models are contained within this box plot. Again, there's the uncertainty, right? So I can't just put a point there because I have 10 different estimates of what this thing might look like. And so what I really want to do is look at this holistic, what does this whole piece of information look like? So for rainfall, you can see by and large, all these sites are and all these model projections are saying more rainfall at every one of these locations. But how that rainfall is distributed changes, okay? For some locations, like Amarillo, Texas up here, we see more rain events that occur, or Charlotte, more rain events that occur. For some of them, let's say Boulder, for instance, less rainfall events, okay? Less rainy days, and bigger dry periods in between events, okay? So let's think about what that means for a place like Boulder, Colorado. I've got more rainfall, but I've got fewer events, fewer days when it's raining, and bigger dry periods in between my events. So it basically tells me I'm going to have less events that are bigger. So more intense rainfall is what we would project, okay? For a place like Charlotte, you've got more rainfall, more rain events, more rainy days, and smaller drying periods, right? And so this indicates that, you know, although we may see more extreme events, we're also going to see just more events in general, more rainfall that occurs. And so you can kind of pick through each of these and basically see for specific locations. Memphis, pretty similar to what we saw in Charlotte, for instance. The other thing that we have to look at is extreme events within that data. And so Matthew basically pulled out these percentiles. What's the 50th percentile rain event up to like the 90th and 99.9th percentile, okay? And what it tells us is how do my extreme or my outlying big events compare, right? And so for 99th, let's say 99th percentile, you can see all of them are big. So the bigger events get bigger, right, is basically what we see inside of our data. Okay, so when we start pulling this data out, it kind of pulls at that point that things are not going to be consistent everywhere. And we can start seeing patterns in how things are going to look in different regions. Okay. So what can we do? And green infrastructure and things like bioretention are being called out as a way to build resiliency into systems. And I think that's true. I think we are able to store more water into in urban spaces with systems like this. But they also have limitations. So after hurricane, one of the hurricanes that hit Houston, I believe, I got interviewed and they were asking me what could be done about this rainfall that happened in Houston. And, you know, it's kind of prodding you like, what do you work on? You know, I do green infrastructure. We're building resiliency. And I had to admit, if it rains 20, 25 inches, there's nothing we can do. You have to get out of the floodplain because, yeah, it's a huge event, right? And so I think like Bill was saying, like understanding some of these implications is important because if you're getting enough rainfall that it's covering over I-40, that's pretty difficult to do anything about. All right, so bioretention schematic, you guys are familiar with what goes on here. What we're going to focus on is how much water in the future is going to go into infiltrating into our system, how much is going to go into a drainage system, how much of it is going to overflow, right? So we basically partitioned our bioretention into these three pieces here. And we really wanted to see, like, first of all, what are the changes that are going to happen? And again, we use this probabilistic approach. We ran these things in SWIM, and we use kind of a typical profile that you would see in North Carolina or Tennessee in that model. And what we saw is that infiltration in general was less in all these locations than historical conditions. Under drain outflow was higher, and then overflow was much higher, as you would expect from a larger number of big events, okay? So again, these are my locations. This is my current level of infiltration, let's say. This is my distribution from those 10 climate events. So it's going to tell me, you know, what's the probability that these 10 events, based on these 10 events, how is that going to compare to these current conditions, okay? So you can see by and large, infiltration losses go down a little bit in between that. And why is that? Well, as we look at things like underdrain and in particular overflow, so a place like Charlotte, if we look at overflow, we expect there to be much more overflow in the future, meaning that the storage within that system gets overwhelmed by some intensity of rainfall and it can't infiltrate it anymore. And so we're going to get more overflow. And what that means is less water available for things like infiltration. But not terrible. In a lot of cases, we're kind of starting to get within our bounds of uncertainty, right? So for something like Boulder, Massachusetts, Fargo, Phoenix, we may not get huge differences. You can see we're kind of within this band of possibilities. Okay, but in general, we expect there to be more overflow from these systems, and so what it tells us again is that there's limitations, and that once you get past a certain storm size, you're going to have trouble controlling those events with traditional stormwater practices. Okay, again, overflow events, higher intensity of overflow events also. So when it does overflow, those are going to tend to be bigger overflow events. All right, and this just tells us annual volumes and how those volumes change. In the interest of time, I'm not going to worry too much about those things. But overall, what it tells us is that in the southern U.S., we're going to have increased amounts of overflow in these southern areas, and not a surprise with the large events that we expect and more frequency of big events. Maybe not a surprise. Midwest and Northeast, same kind of pattern, but less, not quite as large of a problem. And so their weather patterns are probably going to be not as extremely different as ours. Western and Northwest, even less of a problem. So those GIs seem to be able to tolerate things pretty good. All right. So what can we do about this in terms of design modifications? So the other study was from Andrew Turpak, and it basically looked at, this is a lot of information, but it looked at what different things can we change about a system to make it function differently. We could change how deep our media is. We could change our media conductivity. We could change the surface area coming into my system. So my bioretention is 5% of my drainage area, or is it 10% or 15%? Or we could kind of combine those things. So under a high scenario, I could make more ponding in my system. I can make the system deeper. I can make a higher conductivity, and I could make it, you know, bigger relative to my watershed, right? So those were kind of our composites. So that's if I'm starting from scratch and building a new system. If I've got a retrofit design, there's not as much that I can do. Really, I can probably just dig out some of the soil and allow more storage in my system. And so we looked at both of those things to see how they would function. Again, these are our design modifications over on the left. We're going to look at what our current amount of infiltration is, or what percent of our water budget usually goes to infiltration. And then we're going to look at these 10 climate projections to see how that's going to change. We did this for different infiltration rates. I'm going to focus on like this, I think it's like a clay loam or something like that for this exercise, but we also did it for clay. We did it for, I think, a sandy loam also. So if we look at just retrofits, what can we do if we just go back into our system and change it, right? We can see that in terms of infiltration, it's very challenging for us to really get more infiltration with just by changing the height of the berm. But we are able to do some things with our surface overflow, okay? This tells me that if 15% of my the water coming into the system used to go to overflow, Now I'm expecting anywhere from 20 to 30 percent of my water to go to overflow. Okay. And what it says is my berm height is 6 inches. It's going to be a big problem. If it's a foot, it's going to be less of a problem. 18 inches. And then this one's 2 feet. This is the only one where I really have security that I'm matching my historical rate of surface overflow. Okay. It's not a good idea to do a 2-foot berm around your system. So we have to take into account a little bit of this. We have to think about like what's actually possible and what's actually feasible. Okay. Other things that we looked at were if we start from scratch and we build a new system, what might happen? And what we see for most of these is that changing the media depth, changing the media conductivity, changing even the depth of the system didn't have nearly the same impact as something like just changing the way that it's sized to make it much, almost twice as big as what we currently are to reach the same level of infiltration, overflow, and drainage underflow. So what that means is that if we want to take incoming runoff and partition it to infiltration, overflow, and drainage, the same way that we've been doing in the past, the same like water balance basically, we want to keep the same water balance that we've had historically, then we have to substantially change the size of these systems. So it brings about the point of like, what do we expect out of our stormwater systems and what are we willing to tolerate in the future? And this is more of a big like philosophical question, I think, for us moving ahead. What does resilience mean for us? And do we actually expect to have the same water balance in the future as what we've had in the past? Is that what we're calling resilience? And so I think the more that we're able to define what we want out of these systems, the better we're able to find solutions. And I'm not sure that we're there yet, that we know exactly what we mean. Other things that people are doing, I just wanted to kind of expose you to some different things, is IDF curves. So how do things like 25-year storms change? There's a good paper out by Cook, who used similar data to us to look at basically how IDF curves are going to change in the future. There's some cool things like this. This is a project from Cornell. And I think we'll share these slides with you. But if you look at this link, they've basically produced new IDF curves for across the whole state of New York. And so, we're starting to get there and starting to understand the implications of climate change, but there's a lot of work to be done. So I talked a lot about hydrology. There are some other elements that we also think about. We talk a lot about rainfall and extreme rainfall, but this idea of more dry days is also really important for green infrastructure. It's the concept that we may see less frequent events in some locations. So when you think about what that does to our systems, it's a problem. It means that we're going to see drier conditions, which can be a problem for microbes. It can be a problem for plants. We really have to think about what plants we're planting, because that if they're experiencing more drought conditions, they have to be able to handle that. Okay, microbes in particular, this is a concern for, because once microbes start getting influenced, the way they function for things like nutrients starts getting influenced. So this is kind of a sidebar, but this is a project that we did to look at basically how nitrate concentrations vary based on how dry it was leading up to a given storm event. And what it tells you is basically the drier that it's been leading up to a storm event, the higher concentrations that you get coming out of that system. So what this means is that, it only rained like an inch leading up in the month leading up to a given event. And it basically means that we start exporting, or we start having higher nitrate concentrations. This is what we see in things like bioretention cells, is that if they have, if there's been dry conditions leading up to an event, then they can even potentially leach nitrogen for that next event that happens, right? And so there are these things that we care about when we start talking about drought also. And it does influence nutrient and pollutant removal conditions inside of our systems. So I'm probably running over, but thanks for your time again. It's good to see so many friends on here. Feel free to contact me, check out our website and see what we have going on over in Tennessee.
Thanks, John. And while I have you on, I'm just going to answer this one quick, ask you this one quick question that was directed from you, John. It says, "Hi, John. Does this mean that the 90th percentile storm will be getting bigger, and therefore, if we still want to improve water quality from the storms?" Oh, I'm sorry, just moved up here. Oh, this is a long question. Up to the 90th percentile, we will still use the new 90th percentile storm. So that's the first question. Did that make sense? Okay.
I suspect that is the case, that the 90th, 99th storms are going to get bigger. That upper level, upper percentiles are probably going to get bigger. What we're running into now is that you've had climate scientists who are looking at global type of situations, right? So they're looking at global climate. How is global climate going to change? Okay. And then you start seeing research on regional climate and how does regional climate going to change? And just over the few, like maybe 5 years or so, you see people starting to look at like, what does this mean for me, like locally? Okay. And so the first step that you've seen is people starting to manipulate IDF curves to deal with that. But IDF curves don't tell you anything about what you're saying, 90th percentile storms. And so this has not been looked at a whole lot, but yes, it probably does mean that those percentiles are going to go up.
I really love that you came up with this, John, because one of the things that we did, I didn't include in my talk, was look at, and this is not projecting, this is just looking at the 90 percentile storm as it's changed since 2004 when Dr. Evan Bean looked at it, and last year. And we found that in places like Fayetteville and Wilmington, the 90 percentile storm increased by 60 to 70%. And so, in other words, if you take what John said, is that, okay, we'd have to double the size of our practices to maintain the same level of performance. You can even make an argument that we have the tools right now that suggest that you should increase them by at least 50% just based upon the rains that have fallen in the last 15 years. So, and those data actually are present, and there's no sort of wish, it's not like they've been modeled out. These are like, which I'm not discounting because it's so important that's been done. But there are data right now that say we probably should be using, if you're in Wilmington or Fayetteville, 50% more for our water quality size.
Okay. All right. There's a second part. If anybody wants to continue to stay just for a bit, we can answer the second part of the question. Also from Mike, he said, interested in how these potential design recommendations that could improve resiliency could be implemented at the local level, considering the recent proposed legislation, SB 105, Section 12.16. Then it also stated limitations on any local stormwater ordinances that prohibit local stormwater control requirements from exceeding state and federal government requirements. That's
yeah. Do you want me to answer that, John?
That's what I was going to say.
It's a political hot potato, and I will just state facts. The less opportunity local governments have to produce locally specialized ordinances, the less opportunity they have to mitigate flooding. That's pretty much long and the short of it. And I will also say that in the same legislature is looking at giving out hundreds of millions of dollars for communities to implement to implement flood resilience projects. And so Obviously, as a stormwater guy, I love one part of what's being proposed, and I would prefer certainly that municipalities have more flexibility to do with retrofitting and the like. But it is a legitimate and important question to ask.
Okay.
Unfortunately, I think in the environmental field is like environmental legislature tends to be very reactive. And so, for instance, like, why do you have the noose and tar Pamlico rules to begin with? Like, huge fish kills that led to people caring about it, right? And then our conscience kind of wanes over time, and then something else happens. I remember we were all underwater harvesting when there was a huge drought in Raleigh, and then it started raining again, and we forgot about it. And then, in Tennessee, we had Nashville had a huge, horrific. I mean, all of downtown got flooded, and so, right now they're fairly conscious about water quality and water because they have that memory of what could happen. And so unfortunately I suspect that there's going to have to be a number of flood events that happen before people realize that they probably need to consider these.
Okay. Well, thank you guys. I see Annette has popped on. Annette, would you like to say something?
Oh, good afternoon. Yeah, the proposed legislation right now is just proposed. So I'm happy to say not all proposed legislation winds up becoming law. So we have our fingers crossed. And also I wanted to point out that flooding is typically a local government responsibility and not the state. So we're hoping they don't limit local governments to what the state requires for flooding, since we don't require anything in DEQ. So we'll keep you all informed as we know anything happening with it, that legislation.
Okay. Well, thank you guys for logging on. And yeah, I know we went a little bit over time, but it was a good discussion. So again, thank you guys. We do have our next WOW webinar for September the 15th. So please note your calendars for that, and our upcoming 2021-22 WOW webinar series will be on the website soon. So we'll kind of let everybody know what to expect and what's coming in the future, the months as far as that's concerned, other topics I should say. And then what I'll do is I'll let Annette to kind of close us out and see if she wants to add anything to it.
Wonderful. Thank you, Michelle, for doing a great job organizing this. I think this is our record number of attendees. So thank you so much, professors John Hathaway, Bill Hunt. John, it's a little hard to see you with all that UT stuff, but I'm getting used to it. Don't forget where you came from.
One of our SEC rivals said when they come into our stadium, it looks like a bunch of inmates in the audience.
Yeah, that orange. But we're really grateful that you both joined us. You're a great team, and thank you so much. Next month, the webinar will be September the 15th. It will be back to the regular time, 11 a.m. And it will be Wendy Hardup from the town of Kernersville. She's one of our MS4 leaders. She'll be talking about the public education and involvement part of the MS4 program. She may involve some other of her friends from other local governments, but they will present and answer questions on their journey to create and implement a compliant, effective, and fun public education and involvement program. So that'll be kind of a warm up for the APWA conference happening later that month. John, it'd be great if you came to that conference. Think about that.
Oh, this is the one in Nashville?
It's in Nashville, so it's not so far from you. It's closer to you than to me. So anyway.
Yeah, 2 hour from over there.
Yes.
Why don't you come over and we'll have a drink together on Monday night?
Yeah, that's not a bad idea.
Okay.
Absolutely. Well, and thanks to the whole stormwater community of North Carolina. Y'all are awesome.